Proper lubrication is a vital part of any industrial maintenance program. Using the wrong kind of lubricant or using the wrong amount of lubricant can be worse than no lubrication at all. And making certain that lubrication gets done correctly involves more than just using an oil can or grease gun. It requires understanding how different types of oils and greases are used and the functions they serve. And it requires knowing how different lubrication systems work. Whenever components slide or rub on each other, they create friction, which results in heat and wear. Lubricants can reduce that friction and wear because they stick to surfaces and form a thin film for moving parts to ride on, even when the parts are tightly pressed together. Lubrication also carries away heat and contaminants and helps seal and protect metal surfaces against corrosion. In some cases, the actual amount of surface area contact between metal parts is small. This ball bearing, for example, has very little surface area contact and normally produces very little friction. However, the rolling action is not quite perfect, especially when the bearing is heavily loaded or if the balls or rollers are distorted. A thin lubrication film is still essential to separate the parts. More than a very thin film, however, will actually increase the friction. That's right, the rolling elements will have to push the lubricant out of the way as they roll around. It's like wading through mud. The lubricant used in a ball or roller bearing must be able to maintain the thin film without increasing the resistance to movement. That's why knowing the right type of lubricant to use is so important. There are two major kinds of lubricants, fluids and greases. Fluid lubricants are classified according to their source of origin. Mineral oils are made from refined petroleum and come in a wide range of thicknesses for different applications. Biodegradable oils are made from either vegetable oils like rapeseed oil or from synthetic esters. These are used in situations where other types of oils might cause environmental damage. Synthetic oils are made completely by chemical manufacture. There are many different kinds, but polyalkylene glycols, polyalpha olefins, and silicones are probably the most popular. Finally, there is a group of fire-resistant oils, typically hydraulic oils like the water glycols and invert emulsions. These are often used where combustible materials would cause a hazard, for example, in foundries, coal mines, or steelworks. The thickness of an oil, its viscosity, is measured by timing how fast it runs through a standard-sized tube at a standard temperature. The oil is then given its viscosity grade, or VG number, based on standards established by an international standards organization, the ISO. This number, given in centistokes, is the oil's ISO VG number and indicates its viscosity. The higher an oil's ISO VG number, the more viscous it is, and the more slowly it flows at any particular temperature. For example, an oil with an ISO VG number of 320 centistokes or more is heavy or viscous at 100 degrees Fahrenheit. At the same temperature, an oil with an ISO VG number of less than about 46 centistokes is light, and it flows more easily. Notice that the viscosity rating is always given at a specific temperature because viscosity changes as temperature changes. At very low temperatures, oil may not be able to flow into lubrication points on equipment. At very high temperatures, the oil may flow away from the parts being lubricated. So make sure the oil you use has the correct viscosity. The second kind of lubricant is grease. Grease is oil combined with a thickener. The oil provides the necessary lubrication film, while the thickener holds the oil in place so that it cannot flow away from the parts that need lubricating. The consistency of grease is measured in terms of its stiffness. Stiffness varies from 000, which is semi-fluid and almost like a heavy oil, to number 6, which is very stiff, almost like soap. Just as temperature affects the viscosity of oil, it also affects the stiffness of grease. At low temperatures, the oil in a grease may become so viscous or thick that it cannot flow well enough to provide a lubricating film. At high temperatures, the oil in the grease thins out. When temperatures are high enough, at a temperature called the drop point, the thickener itself will usually melt. Once grease is melted, it may not return to its original consistency, even after it cools. Sometimes the stiffness of grease can change, even if temperature remains the same. For example, stiffness may change if different greases are mixed together, and some poor quality greases will become more fluid if worked or churned vigorously. When this happens, the grease may permanently change and may no longer be suitable for the application. Grease may also become stiffer if too much oil bleeds out of the grease. Some bleeding is normal because that's how the grease provides its lubrication film. But if too much oil bleeds out, the remaining grease will be dry and hard, unable to provide the required lubrication. It will have to be removed and replaced. To improve the properties of the oil and grease for particular applications, lubricant manufacturers often include additives. In applications where gears or other moving parts may whip air bubbles into oil, anti-foaming additives help release the bubbles quickly. Many oils and greases include special additives to prevent oxygen from combining with metal parts to form rust, and to prevent oxygen from combining with the oil. However, even with these additives, oil or grease will oxidize if it is kept hot enough for long enough. When that happens, the oxidized oil or grease will lubricate poorly, and they may corrode some kinds of metals. Oxidized greases and oils are usually easy to identify. Oxidized grease becomes dark and dry. Oxidized oil is darker, thicker, and it feels less slippery. Oxidized oil may also smell burned. Now remember, we said earlier that proper lubrication is a matter of using the right lubricant in the right amount at the right time without damaging anything. This is especially true when it comes to grease lubrication. Keep in mind it's more important not to damage seals than to add a lot of new grease. If old grease cannot get out as new grease is added, pressure will build up. So before you begin, look closely at the equipment to see if there is anywhere that the old grease can come out. In some installations, a vent plug is provided. In many cases, grease can vent without damage. There may be nothing more than a simple shield plate to protect components from dirt. Grease can push by it easily, and there is no danger of building up grease pressure inside the component. Many types of seals will also allow grease to vent if it is added slowly and carefully, but adding it too fast can damage the seal. Labyrinth seals, for example, consist of a series of interlocking grooves or plates which allow grease to squeeze through. Felt seals will push aside under pressure. Rubber or plastic seals like this will also usually allow grease to vent slowly without damage. Be careful though, too much grease pressure can pop them out. Pay attention to the feel of the grease gun. If it pumps easily at first, then stiffens up after a few shots, stop. The bearing is probably full. In the case of a rolling element bearing, remove the grease nipple temporarily and allow the bearing to purge itself while the shaft turns. You may also find rubber shields or boots on some kinds of joints. Some will allow grease to vent, some will not. If you see the boot swelling as you add grease and no old grease comes out, stop. Lubricating a machine with oil is different than lubricating with grease. There must be a reservoir where oil is stored, and there must be some method of delivering the oil at the right rate to where it's needed. Both parts of the oil lubrication system require careful attention. The oil in the reservoir must be kept at the correct level, and the delivery system must be kept working properly. Sometimes the reservoir and the delivery system are the same. For example, rolling element bearings are sometimes lubricated by running in an oil reservoir built into the bearing housing. Usually, the oil level should be no higher than the midpoint of the lowest roller or ball when the shaft is stopped. If you try to add oil when the machine is operating, however, you may overfill the machine since some oil is spread around inside the housing. When the machine stops, the excess oil may run back out, or too much oil could produce extra friction in the machine. Plain bearings sometimes use a reservoir built into the housing. In low and medium speed machinery, a ring, chain, or collar brings oil up to the bearing surfaces. The reservoir level must be correct. If the oil is fairly viscous and the oil level too high, the shaft will not be able to pull the ring or chain around properly. And if the level is too low, not enough oil will be brought up. In some equipment, oil is delivered by splash. In this gearbox, for example, the gears are lubricated as they rotate within the oil reservoir. In engines, compressors, and some large machine tools, oil is circulated from the reservoir under pressure by a pump. Since the oil level will drop when the machine is running and may rise as the oil warms up and expands, manufacturers usually specify under what conditions the oil pressure and level should be checked. To make checking the reservoir easy, many reservoirs have a sight glass to indicate the proper level. Some sight glasses have two levels marked, one for when the machine is running and the other for when the machine is at rest. Be sure to read the proper mark when checking oil levels. All the oil delivery systems we've described so far allow the oil to be recycled. That is, the reservoir is also a sump where oil returns after it has been delivered to the bearing parts. Some oil delivery systems use the oil only once. This drop feed oiler is an example. It delivers oil one drop at a time, and its external reservoir must be refilled fairly frequently. Similarly, cup oilers are used to supply a controlled feed rate, but they use a needle valve to regulate the oil flow. Cup oilers, like other oil delivery systems with small reservoirs, need to have the oil level checked frequently. An oil mist system also uses the oil just once. Dry, compressed air generates a mist and carries the lubricant to the component. There are many other ways machinery is lubricated, from simple hand spreading of grease to spray-on dry lubricants to sophisticated automatic pumped grease systems that almost eliminate manual lubrication in some plants. Now, a word of caution about lubrication. Do not try to lubricate equipment which does not need it. Many rolling element bearings are permanently sealed and lubricated for life. These require nothing but periodic inspection to make sure the seals and shields are doing their job. If you don't see an oil cup, hole, cap, reservoir, or grease fitting, don't try to lubricate the component until you are absolutely sure of the proper method of lubrication. Finally, preventive maintenance and troubleshooting. Another important part of your work is spotting potential problems with the machinery you are lubricating. In some preventive maintenance programs, routine inspections may be an official part of your job. You may be in the best position of anyone to notice bearings or gears that grind, whine, thump, or knock, and machinery that is vibrating, rubbing, or out of alignment or adjustment. Unusual or excessive heat is also a sign of a problem. In a plain bearing, inadequate lubrication is a common cause of heat. In a rolling element bearing, heat can mean over-lubrication as well as under-lubrication. The condition of oil and grease may also indicate problems. We saw earlier what oxidized oil and grease look like. If you rub some used oil or grease between your fingers, you may be able to see or feel the presence of water, grit, metal flakes, or other contaminants. If your facility has a predictive maintenance program, routine oil samples will be taken and analyzed. These periodic samples will allow wear and contamination to be spotted much earlier and much more accurately. In this lesson, we have seen the common types of lubricants, examined their characteristics, and seen how they are used in modern industry. By applying the principles of proper lubrication in your workplace, you will almost certainly extend the life of mechanical equipment and reduce the occurrence of lubricant-related failures.